0.6 is a review of the properties of exponents. So that's our learning goals. I can apply the properties of exponents. And then we also want to be able to graph exponential functions. So we'll be reviewing through that. Just to review our exponential function, first of all, we'll talk about what an exponential function is, right? This is an exponential function represented by a constant base and a variable exponent. So for example, right here, 2 is my constant base, and then my variable is up in the exponent. Or e is my constant base, my variable is x. Or in this one, I have 3 as my constant base, and now I just don't have an x up there, I have an x squared minus 5. But again, my exponent is a variable exponent. In this case, it's x squared minus 5. It changes. So here's the basic properties we work with when we work with exponential functions. And you guys are already familiar with, you should be familiar with all of them. We'll just do a quick review, right? A to the 0 power is 1. If I multiply two things with the same base, we add their exponents. The third one is if I divide things with the same base, the base stays the same and I subtract the exponents. Fourth one, if I have a power to a power, I multiply the exponents. Fifth one, if you have parentheses, as long as you're multiplying on the inside, the exponent just applies to both of them. So a to the x, b to the x. Or the sixth one here, right, if I'm dividing on the inside, again, the exponent just applies to both of them. If you do have a negative exponent, like here on number 7, you can take the reciprocal. You can flip it over. So a to the negative x becomes 1 over a to the x. Now, notice we talked about this already, but if I have a plus on the inside, I cannot just raise both of them to a power. We've actually talked about that a bunch. When you square a binomial, right, we talked about you cannot just square the x and square the 5. And the reason why is because they're added together, rather than up here they're multiplied, and right here they're divided. So with addition and subtraction, that rule does not apply. So just be careful with that. When we're simplifying, you do not leave answers with negative exponents. Okay? So if it says to simplify, do not leave answers with negative exponents. Okay, let's go through and work down through and simplify these. So number 1, I have 27 to the 4/3 power. So this is a good review. This is something that actually was not on that list, but you guys have done it a lot before. If you have a rational exponent, a fraction of the exponent, you can actually rewrite it as a radical. Hopefully we remember doing this. The 3 goes there, the denominator goes as the index, the 4 goes there, and you can either put the 27, 27 goes there, the base goes on the inside, and then you can put the 4th power on the inside or you can put the 4th power on the outside. It doesn't matter which one. Because 27 to the 4th is really big, I'm going to do the cubed root first and then the 4th power second. All right, cubed root of 27 is 3, and 3 to the 4th power, that's 3 times 3 is 9, times 3 is 27, times 3 is 81. 3 times 3 times 3 times 3 comes out to be 81. Okay, number 2, that 0 applies to that entire thing, so it's equal to 1. 0 power equals 1. On number 3, I'm going to do some simplifying here. So first, you could square everything on the inside, but I'm first just going to simplify that top part. So e to the 5th times e to the negative 3 would be e to the, and the rule was we add the exponent. So 5 plus negative 3 is 2. Okay, now I'm going to use the second rule, the other rule, which is the quotient rule. If I'm dividing things with the same base or both base e, we subtract the exponents. So that'd be e to the, and I go 2 minus 4. Okay, now I have a power to a power, right? E to the negative 2 squared. You multiply the exponents. And that's my answer, but the very last thing we said is don't leave negative exponents. So the very last thing is I'm going to take the reciprocal. Now, there's a lot of other ways you could have done that if you wanted to. You could have just squared everything on the inside. You would have got e to the 10th, e to the negative 6, e to the 8th, and then you could have combined them together. You would have ended up with the same thing. So a lot of times, and that sometimes makes it challenging, a lot of times with exponents, you can apply the rules in different orders. You just have to be careful that you do one step at a time, and usually we make less mistakes with that. Okay, number 4, if I have 5 to the 3rd times 25 to the negative 2, and remember we're not supposed to use a calculator, I'm going to leave that as being 5 to the 3rd, and I'm going to move that 25 to the negative 2 down below. Now it become 25 to the positive 2. Let me just fix that. And now, 25 squared is a big number. I'm not sure what it is. I don't want to multiply that out. So what I'm going to do is a little trick here is I'm going to go 5 to the third. I'm going to write 25 as being 5 squared, and I still have that square on the outside. So the 25 right there became the 5 squared right there. And the reason why I did that is because now I can simplify it, right? I have 5 to the third, and 5 squared squared is 5 to the fourth. All right, now I can apply my rule. If I'm dividing two things to the same base, the base stays the same. Subtract the exponents. It's always the top minus the bottom. So 3 minus 4 is -1. Flip it over, 1/5. Now, if I wanted to over here, if they're both positive exponents right here, I could just cancel out those 3 5s with 3 of those, right? You'd end up with no 5s left on top, of 1 goes there, and there's 1 5 left on the bottom. And that's fine. You can just think of it as reducing factors, as long as they're positive exponents. If they're negative exponents, then we can't do that. Okay, let's do this last problem, this number 5. Solve 9 to the x equals 27 without using a calculator. So if I don't have a calculator to use, the easiest way to do this is to try to rewrite them with the same base. What I mean by is, can I write them both as base 9? No, I can't write 27 as being 9 to a power. Well, what could I write 27 as? Well, I could write 27 as being a base 3. Right, I could write 9 as being base 3. 9 is 3 squared, and 27 is actually 3 to the third. So I'm going to write them both with a base 3. That's one of our strategies for solving exponential equations. So 9 is the same as 3 squared to the x power. 27 is the same as saying 3 to the third. Okay, now I'm going to use my properties, to simplify this. 3 squared to the x power, that's a power to a power, so I multiply those. If I can get it like this, they both have the same base. Now just think about this. We know that they're equal. I have an equal sign there, and I know they both have a base 3. Well, the only way they can be equal and have the same base is if their exponents are equal. So if you get to that point, now all I have to do is go, I know 2x equals 3. You solve that equation. And we're done. Okay, we don't have to go any further. So that's one strategy. There's some other strategies for solving exponential equations, but they involve logarithms and you need a calculator for it. So without a calculator, that's our option, is we're going to try to make it always so that they have the same base. And then once they have the same base, we can set their exponents equal and solve it from there. All right, we're going to really quick, I want you to grab a graphing calculator. If not, grab your phone or a computer. You can go to Decimals. But I want you to graph these 3 functions. Graph y equals 2 to the x, y equals 5 to the x, and y equals e to the x. Graph them in the same coordinate plane. And then I want you to look for similarities. Write down all the similarities you can find. So pause this, go ahead and do that, and then we'll talk about it together. What you should have seen is 2 to the x crossed at 0, 1. If I plug 1 in there, it crosses at 1, 2. So 2 to the x comes in like this. Y equals 5 to the x, it still crosses at 0, 1, but your next point, when I plug 1 in there, that'd be 5 to the first power. You'd be up here at 5. So it should have come in something like this. Okay, so that's the 5 to the x. And then the last one, e to the x. E to the x is about 2.7. Well, if I plug 0 in, I still get 1, but my next point would be at 1 and about 2.7, somewhere in there. So it's somewhere between those two graphs that it's coming up like that. So if you look at common things, and we want to get common things so we know what these graphs look like. So some things you see in common is they all have a y-intercept at 0, 1. They also all have a point at 1, and then whatever your base is. So if I write this up here, y equals a to the x power, they always have a point at 1a. And what I mean by that is the first one had a base 2, so there's a point at 1, 2. The second one had a base 5, so there's a point at 1, 5. The third one had a base of e, so there's a point at 1, and e is about 2.7. Other things you may have noticed is all these functions are increasing. Right, from left to right, they're going up, they're increasing. They all have a horizontal asymptote as I go to the left. In other words, this is the way you write that, if you remember this from last year. As x goes to negative infinity, that just means as I go to the left, the y value gets closer to 0. So as I go to the left, I'll trace along here on all of them. As I go to the left, I'm getting closer and closer and closer to 0. And that's all that means. So here's kind of a list that our book has. right? The domain, they're both negative infinity to infinity. The range, it starts at 0, does not include 0, so there's a parenthesis, so it includes 0 to infinity. We said these, right? They're continuous. They are increasing. Hey, concave up means that it's like a smiley face. So if it's concave down, it's like a frowny face. Concave up is like a smiley face. It's always concave up. This is a one-to-one function, right? It passes both the horizontal and the vertical line test. 3, it says there's a horizontal asymptote as I go to the left. This notation we haven't used before. What this is saying is as x goes to negative infinity, y, or f of x, goes to 0. It's really the same thing as I wrote. This is using something called limit notation, which we're going to get a lot into in our next chapter. See the little star down here? So we're not going to worry a whole lot about it right now. A couple of points, we said this, have a point at 0, 1, and at 1a. All right, so it says use, hold on, did I skip one there? There we go. It says the letter A used in examples 2, 3, and 6 is not an unknown, right? It's not a variable. It's a number called the natural base, okay? And it's used a lot in calculus. So when we get into taking derivatives and integrals of exponentials and logarithms, we'll mainly do base E. Base E was discovered, right, or it comes from this. And again, this deals with the notation, that limit notation. So we're not going to worry too. When we get to limits, we'll come back and talk about how E was discovered or how it's found. But the idea is this, E is about, if you go out 3 decimal places, it's 2.718 is what it comes out to. Okay, so it says without using a calculator graph, sketch graph of y equals e to the x. All you do, right, we know it has a point 0, 1. We know it has a point 1, 2.7. We know it has a horizontal asymptote, and it's always increasing. There we go, we're done. So I don't want you spending tons of time in this graph. I really just want these 2 points, 0, 1, and then 1 and whatever your base is. We know there's a horizontal asymptote. We know it's always increasing. Now we can take these graphs and do adjustments, so we can change things. So these follow the same rules that we've already learned for transformations. So it's using adjustments to the graph from example 7, graph f of x equals e to the negative x plus 1. So we're taking that same graph and adjusting it. So we have 2 transformations here. One is that we had that plus 1, and that plus 1's on the outside of the function. When you think of an exponential, let's come down here. If I have y equals e to the x is the inside. So anything that's on the inside has to be up here with the x. So if there were a plus 1 up with the x, that would be inside and move it left or right. But this is on the outside, so it's moving it up. It does, however, have a negative up there, which means it's going to reflect it about horizontally, right? If the negative is with the x on the inside, it reflects it across the y-axis. So if we come up here, let's start by just reflecting it. Let me do a different color because I hate that green. We know it has a point at 0, 1. If I reflect that across the y-axis, it's still the same point. Usually it'd have a point at 1 and 2.7. If I reflect that across, there'll be a point at negative 1 and 2.7. Instead of having a horizontal asymptote going to the left, when I reflect that, it's going to have a horizontal asymptote going to the right. So my graph's going to look something like that. It's just reflected across. Now that's without the plus 1. Okay, let's go ahead and do the plus 1. So I'm going to take all those points. I'll do a different color and move it up 1. Instead of being at 0, 1, it's at 0, 2. Instead of being at negative 1, 2.7, it's going to be negative 1, 3.7. And instead of having a horizontal asymptote at 0, as I go to the right over here, it's going to have a horizontal asymptote at 1. So it's going to come like this, come along there, and curve along. Oops, kind of went down too far, but it's curving along there. Okay, so all those same adjustments that we've already done, they're no different using those same ones. And that's pretty much it. On this assignment, you're just practicing exponent rules. That's the first thing. The second thing is you will be graphing exponential functions using those adjustments and those different things. So it takes a little bit of practice, but that's what we're here for, is right? We're just, this whole chapter, we're just reviewing and making sure we have all this down. Thanks, guys.